This is a panel discussion on DOE and academia. We are talking about how the four fine gentlemen on your screen teach design of experiments at their schools and how they effectively build scientists who know what they're doing when they get into industry. So let's go ahead and get some introductions. Just a quick who you are, where you're from, what you're excited about when you teach DOE. Johannes, do you want to start?
Sure. So my name is Johannes. I'm a biotechnologist and bioprocess engineer by training. I'm from Germany, but currently teaching at Bochum University in Vienna, Austria. So I'm from across the pond. And my motivation and inspiration is that it's always very interesting to see the faces of people when you tell them, okay, you can cut the number of your experiments, say by half, and still get more information and knowledge and understanding of the things that you're doing, of the processes that you are developing when using DOE instead of one factor at a time approaches.
Thank you. Mark?
Good morning, everyone. I'm Mark Ruscombe, and I teach at Fair State University, which is located in a small town kind of in northern Michigan, Big Rapids, Michigan. We're an engineering technology program, so we focus on hands-on learning. My students do a lot of machining in their program. My students ultimately are manufacturing engineers, and so that's what the program focuses on, is application of design experiment in a manufacturing setting. We tend to do a lot of hands-on experiments during the class to facilitate that learning, and we use studies to as the tool of choice for doing all of our analysis.
Thank you. Tom?
Hello, I'm Tom Keenan, and I am a retired professional industrial statistician, and I'm an adjunct instructor at the University of St. Thomas in St. Paul, Minnesota. And for their School of Engineering, they have two stat courses. One is a semester-long course in design of experiments. And I'm excited about that because I believe the DOE lies central to the scientific method itself.
Thank you. And last but certainly not least, Dave?
I'm David Dixon. I'm a professor of chemical engineering at South Dakota School of Mines and Technology. It's a small school, engineering and science related, and we're on western South Dakota, maybe 30 minutes from Mount Rushmore, if you're familiar with that. So most people don't get to South Dakota, but if you ever go there, that's a nice place to visit. So we're close to that. I got excited about design of experiments when I was in industry for a little bit. I worked in a company in Michigan, and we were using this in an applied mode to learn more about our experimentations. And that's what I've tried to do with our students, get them, I guess I should back up, most of our students graduate with a bachelor's degree and go into industry. And so we like to give them more of an applied focus. They certainly get the technical background, but then how can they take what they learn on the design of experiments class and apply that in an industrial setting? And the company that I used to work for used StatEase, and when I contacted them, they said, yeah, that's StatEase is what we use. And so that's been what I've worked with now for the past 20 years to introduce the students to that.
Thank you. And let's start off with you, Dave, for the first question, because StatEase has come to South Dakota Mines to help you teach DOE for the last at least decade, as long as I've been with StatEase. Can you talk about the statistics curriculum that you guys teach and how DOE fits into it?
Yeah, I sure will. When I first decided, I thought our students needed to get into and get exposed to the design of experiments. We were very small in terms of the faculty numbers, so we didn't have a lot of bandwidth to teach more classes. And so as I mentioned before, I talked to my company. They said, yeah, they work with StatEase. So I called up Mark Anderson and proposed to him if he could come and give us a condensed version of some of the courses that he teaches for StatEase, and basically his books, he was working on those. And so our students get introduced a little bit to statistics just through the other courses that we teach, but they hadn't been exposed to design of experiments. We do have a course on our campus that's the full-blown, I would say, design of experiments, statistics, and all of the math behind that. But we didn't have a way to get that into our curriculum. And so the shortened version of the courses that you can take with StatEase were what Mark and later Sherry brought to the table. So they would come out for a couple of weekends, basically long weekends. Our students had to come in on Saturday. Now we've gone to a virtual one with Mark, and that seems to work very well. It's a very condensed version, so the students can get their exposure to this and do some practical exercises. That's sort of what we do now. We've done that, I think, now for 20 years. Even through COVID, we did the remote version with Mark and Sherry.
We love coming out to teach. Your students are always very excited. How about everyone else? What kind of statistics curriculum do you guys have, and how does DOE fit into it?
So our program, again, my graduates are working for a manufacturing engineering degree. The DOE is built right into the degree requirements, but to get to it, you have to ramp up through a first statistics class, a basic statistics. Of course, our math department teaches a stats class, our business college teaches a stats class, but our College of Engineering Technology, we teach our own version of stats, and mostly then what we can control is the examples that are used in class. The big thing that we want to get through, of course, to lead into DOE is the hypothesis tests, and in particular ANOVA. And then there's a stats 2 that really is more applications, sort of the SPC, the statistical sampling, things like that. And then in their third term, they would take the DOE as sort of the capstone event for the statistics. And then the way it fits in to the broader college is there's a 4-class certificate, those 3 classes. Then we teach a class in metrology, which covers gauge R&R and linearity studies. GD&T is included in that. And so with those 4 classes, they can earn a quality certificate. And so that's sort of how we spread the gospel of DOE and how important it is. We have a welding program, for example, and for welders, DOE is perfect for solving their problems. We have an automotive engineering program. The automotive engineers have those 4 classes built directly into their program. So there's a very clear path for all sorts of students to be able to access this tool.
Is that similar to either of your programs, Johannes or Tom?
I would think so. Yeah. So we also have like basic courses in math, and then some more applied courses on statistics, and combined with applications in statistics. So this is like a split course. Like you would, in one part, you would get the background and fundamentals of statistics, and in another one, you would do like actual practical examples. These are sort of the base layer of information we convey to the students, and then building up on that, we have set up a new curriculum. I forgot to mention it, so I teach in a biotechnology and food sciences environment. For that, we have set up a new curriculum where we have specific module on bioprocess development, and DOE, at least the first parts of DOE, like screening experiments, is one part of it. And that's part of the bachelor curriculum, and most of our students continue with the master's. So in Central Europe, you would typically do a master's before doing a PhD. So the master's is quite common. And in the bachelor's, we have, say, the fundamentals of DOE, including the screening designs. And then in the master course, we have a similar module where we teach then the response surfaces, mixture designs, combined designs. And for persons that come from outside and may not have attended these modules because they're not like elective modules, we also have for the PhD students in a combined course where they can catch up on DOE if they want to build that into their thesis.
Rich, I'd like to jump back in. What Johannes just said sort of sparked an issue for me. We teach 2 levels of DOE, actually. Our manufacturing students and sort of the broad population gets DOE 1. which is almost exclusively just two-factor or two-level factorial designs. Then people who are going into a quality concentration can elect to take, or they don't elect, it's included in their program, DOE 2, and then that's where we get into some of the more fun topics that Johannes was talking about: mixture designs, multi-level designs, crossed and nested designs. So there is two levels for that we teach. But in my opinion, and really sort of based on conversations with Mark Anderson years ago, that really, 80 to 85% of what you want to do, you can really do with just two-level factorials. It's not till much later that you get into the higher level, higher order experiments.
So Tom, do you want to talk a little bit about your statistics curriculum?
At the University of St. Thomas, at the undergraduate level, there are degrees in mathematics, statistics, actuarial science, and data science offered by the College of Arts and Sciences, and I'm unrelated to that activity. So I'm an adjunct instructor in the School of Engineering, and at the graduate level, there are two statistics elective courses. One is a semester-long course in DOE, and then the prerequisite for that is called Statistical Methods for Manufacturing Quality, and that course sets the stage for probability distributions, hypothesis testing, analysis of variance regression, introduction to DOE, and a lot of statistical quality assurance.
Awesome, thank you. So everyone knows that the best way to solidify your learning is by practicing the techniques, not just hearing about them in lecture. So what sort of hands-on work do your students do with DOE to make the lessons stick?
I'll go first on that because I think this is sort of one that I prompted in our email. So we do a lot. Within the 15-week term, we will do 4 experiments in class with the students. Get into small groups and they plan the experiment, and then they actually execute the experiment, gather the data, and then we start the analysis. So we have catapults. Probably everyone has seen catapults. You can either buy them online. These actually inherited from a instructor who was before me and then eventually retired, and so I took these over. So we shoot catapults. We shoot it as a full factorial, and then we shoot it as a fractional factorial, so they can compare the results of that. We do then some interesting things. We do a very, very simple experiment where we're just using lengths of pipe to put things together, and that helps us understand what goes into the model. We do another experiment where we run an entire full array, and then we create the half fractional array, and that one is dropping paper helicopters from a mezzanine. We've tried paper airplanes, but throwing paper airplanes results in a lot of noise. So dropping paper helicopters sort of reduces the noise, and we run the full experiment. Then we set up the half fractional, and we extract the data over, and then we can sort of do that side-by-side comparison. What are the results from my full and my fractional? And we will do essentially explaining confounding, the effects of confounding with that. We do and then we do, each student is required this is a senior level class for us, so they're required to do a term project by themselves where they decide on and create their own experiment. I've had everything from people shooting potato guns to cooking hamburgers and making cookies, and shooting bows and arrows and shooting paintball guns. And I had one young lady who was shooting, she set up bales of straw to shoot her bow and arrow, and wound up shooting through the garage door. So we've had some interesting results from that, but very much a focus on hands-on experiments, which then every student is required to do a lab style report on those results. So that's how we provide the hands-on learning portion.
I was interested, Mark, to hear all the things you do. That's really great. You do that over that time frame. We're a bit more compressed, so we start out doing some simple examples along the way. Some of those come out of the book we've used. I asked the students just to get some references in their hands so they can put them on their bookshelves and carry them with them and have some examples. We do use both of Mark's books, the DOE Simplified, which we tend to go through with Mark and the other folks that have come out here. almost all the way through that, and then touch a little bit on response surface methods. So we use some of those examples in the book just to give the students some practice, get used to what the different types of two-level designs are and screenings are. And then when Mark comes, or when Mark works with us in his class, he has some very nice examples that he uses, I think, every time he teaches the class. And they come from all kinds of different industries, which for us is good because the students sometimes touch on things that they know about, sometimes things they don't, but could get into a position doing that. I also have them do a microwave popcorn. It's an experiment Mark has done and Studies has published on before. And so the students get to, try it, taste it, see if it works, or usually costing them, we've only had one fire once, but we've never destroyed a microwave like Mark did. And then we culminate with the paper helicopters, like Mark Rusko said. And that is, we have a balcony. The students go through the design over a few days and see if they hit the target. A little bit of a competition to see how that works. So that's always fun. And the grad students in the class, I do ask them to come up with an example of how they might or will use this in their research. And so that's been nice. We haven't followed up on that yet, but I do believe some of them have used that.
I'd be interested in hearing from the other guys what books you use. David, I have Mark's book on the shelf, but we actually use a Quality by Experimental Design. It's by a guy named Tom Barker. And the reason I like that is there are no partial derivatives in it. It seems like every book I open, I go to a page and there's partial derivatives, and Barker is very, very algebraic and very straightforward. He's had a lot of industrial experience as well. So
yeah, that's good to hear.
That's the book that we've been using for decades.
Very cool.
The book we use at St. Thomas is Douglas Montgomery's Design and Analysis of Experiments, 10th edition, published by Wiley. I think that's excellent. It's full of case studies. So we have a very applied course. It's a case study approach, and we meet 14 times for 3 hours in the evening. So that affords us the ability to embed 3 different physical experiments. We start out by shooting catapults, of course, for a 2-level full factorial. Then later we graduate on to 2-level fractional factorial, following George Box's paper helicopters. And then finally, when we get to response surface designs, we have physical trebuchets, which are very fun and require either central composite design or box bending design. And then also, I'd like to note that the catapults are ubiquitous for DOE training and industry. So when anyone shows up to my class and rolls their eyes at catapults, I have a special surprise, because I purchased from Leonard Lai, a DOE golfer, and that works terrific as well as a substitute full factorial experience for people that already come in with catapult experience. And then one last note. In addition, students are required to conduct a project of their own on any topic. And there have been some, that's the most fun aspect of the course for me. There's been some fantastic DOE projects, including food and beverage designs. And so that's been a lot of fun. There was one team that was inspired by Mark Anderson's beer mixture experiment. And so they did their own cocktail mixture experiment, and I actually showed them the famous John Cornell Harvey Wallbanger cocktail mixture published results. But that team made me very nervous.
What was nervous about it?
Well, they were mixing cocktails.
And then driving home after class.
No, I made it clear we weren't going to do that on campus.
Oh, that's true. The trebuchets is interesting because I also have a trebuchet, but the problem I find with that is you need a counterweight to make the thing go, which means then, my program is taught in 2 locations. So I teach on our main campus. I also teach, which meant I have to carry these heavy weights around. So that's why I default to catapults, because rubber bands are much lighter to carry than those counterbalances.
That's very true. The trebuchets are heavy, yes.
Mm-hmm.
So I have to be very frank here. We hardly have any hands-on experiments for the students in class, unfortunately. So what we do bring is quite a lot of data from our research, and not in the beginning, it's like the nice and shiny results where it's easy to build the models and to see how it works. And then we have, like, I'd say at least a third of the time dedicated for the students using the software and testing their own skills when it comes to analyzing the data. And then, of course, they get examples that are not that nice and shiny, but where there are some pitfalls, and yeah, some of them trap into it, other manage to navigate around it because they actually really carefully considered what we had been discussing before. So it's a mixture of theoretical input and then hands-on analysis of the data. What I do is all the students that start in my lab to do their graduation, like either a bachelor or master thesis, they would always be exposed to the topic and at least have 2, 3, 4, 5 experiments that they plan, conduct, and analyze using design of experiments. So whenever there's a student in my lab, they would do it hands-on, but in the actual teaching course, there's unfortunately not the time to do this sort of hands-on experiments. Yeah.
Yeah, I just have something important to add on to my previous statement, and that is there is a fantastic website offered by Sigma Zone that has virtual catapults. So we actually give our take-home exams using, students are required to do factorial design with a virtual catapult, which would work very well for people teaching online. There's also a virtual trebuchet. And then the Sigma Zone publishes other software for different virtual simulated settings that are really excellent for conducting experiments.
Is there a cost to that, Thomas?
No, you could type in, if you just type in Sigma Zone virtual catapult, you'll start shooting within 10 seconds.
Okay, very cool.
You shouldn't have said that because now everyone online is going to be.
But what I love about that is it shoots the ball, but it doesn't give you the measurement. It actually, the ball comes to rest next to a tape measure. I love the fact that students have to read the tape measure because that is a perfect opportunity to discuss measurement error and its impacts. Oh, and there's randomness built into the virtual catapult. The virtual trebuchet is deterministic, but I mean that affords another discussion about computer simulation experiments.
That seems like
When
a
I
very
do the
nice.
catapult. Oh, go ahead, Johanna. Sorry. Go ahead.
No, I was just going to say that this sounds like a very good thing, and actually that would allow us to build some experimental parts into the lecture as well. So that's a very nice hint, Thomas. Thank you.
Yeah, what's neat is every student generates their own data set, and every student has a different data set, which is different than mine. And the remarkable thing, of course, is maybe not so remarkable. There's enough noise to make it clear that there's uncertainty, but the signals overcome the noise, and so we all get the same conclusions.
We do a similar thing. I have 2 catapults, and I'll break the class into small groups. And then when I'm done, I will take all the results and we'll put all the result, all of their y-intercepts and all their slope for factor A and all their slope for factor B on a graph. We can compare and say that and show very clearly that just because you did the experiment, you think that you have the slope, you really have a slope. And,
Right.
And that's an important thing. Thomas, I'm glad to see that has some noise built in. Otherwise, you'd get everyone has the same slope, and it doesn't illustrate the whole purpose of
Right.
or the whole point of analyzing for noise.
Yeah, and then when we go over the results, each student has one result, and if there's 10 students, then I present all of their data combined with mine as an 11 replicates with 11 blocks.
Oh, okay.
And then that's really neat because we can discover wayward students, if you know what I mean. If the block effect is significant, that's bad news for some student.
And I have it up on that screen. I want to start shooting catapults now, but I'm going to try that pretty when we're done here.
We had tried catapults earlier on, but the ones that we had were built in a freshman class, and they would launch more than 100 yards tennis balls. And that doesn't work well in South Dakota in the middle of winter either. So, but you guys in Michigan and
Yeah, same thing.
Minnesota,
Yeah,
same
my
issue.
catapults are this big, this long, and the arm is 12 inches long. So, and we're shooting hacky sacks. So,
Oh, not too bad.
So David, you make a good point that if you're going to start thinking about implementing some of the stuff, you have to think that through before you go get a, something that can throw a pumpkin 200 yards.
Yeah, yeah.
My students with the potato guns face that issue because of course, they want to build the biggest potato gun they can and then shoot, and it shoots out of sight. And well, how are you going to measure that? So.
So we've kind of started moving into our next topic with discussing the kinds of tools we use, because everyone here is using studies software, and some folks are using the books published by Mark Anderson. I know some of you also use our e-learning to supplement what you're doing. What other tools and software and books do you use, and how does it all fit together?
We start our students off in Excel. We're just now introducing studies, but what we do is essentially we picked a two-level 3-factor experiment, and they build an input table where they can put in the factor names and the levels, and then it populates the array. And then for analysis, in Barker's book that we use, he lays something out I've never seen anyone else talk about, but it's called Yates analysis. And Frank Yates was Fisher's BFF back in the day, and it's an algebraic method to arrive at your sum of squares. It's very non-intuitive, but it's easy to build in Excel. It's all based just on addition and subtraction, and then at the end, take your number and square it, divide by 8, and there's your answer, which is like, how'd that work? But and then we go ahead and we build essentially the half normal plot that you see in studies. I have them build a simplified version of that in Excel, and then we do an ANOVA table, so very similar to what they will see in studies. And so by the time we get to studies, they've seen all this. We build the main effects graph, we build the interaction plots. So we ramp our way up towards studies because for our students, Excel is a huge tool for them to use in industry. So we take advantage of DOE to teach Excel and then extend that into, and then lead us very gently into applying studies. And then, of course, when they see studies, everyone's mad because I made them do all the Excel stuff, and they see how easy it is in studies. But, we've been doing it for 25 years, and I'm not going to change now.
Did you guys develop? Go ahead.
I was just going to say, as I indicated, the book that we use is actually somewhat different. It's Barker's Quality by Experimental Design, which again I inherited from a previous instructor, but I like it. Sorry, David.
No, that's fine, Mark. I was just going to ask. So, do you have a reference or a book that helps the students go through the Excel setup?
We start. Remember, I had said there was sort of this 3-class or 4-class certificate. Mm-hmm. We start in the very first one, introducing them to Excel as standalone assignments. Go into Excel and make this graph. Go into Excel and sort of levels the ground, and then we continue to apply Excel. So by the time we get to this class, it's just something I lead them through. Now, with the advent of online learning that we all got to experience with COVID, I have recorded videos. So I'll go through it quickly in class, and people always struggle to keep up. But then I'll send them off to, just go watch this video. And the students actually appreciate videos that help them construct Excel spreadsheets because they can pause, they can rewind, they can stop and zoom in on, what exactly is this formula.
Okay, yeah, that's good. Yeah,
the other interesting thing.
Go ahead.
Very quickly, I told you I teach in 2 locations. The main campus is very traditional college-age students. The second, the branch campus, is actually working adults. On campus, I have to convince the students that they want to learn Excel. My working adults, I never have to convince them. They understand the power and importance of learning Excel for their job.
Mm-hmm. Yeah, that was interesting what you do. I think we use a bit more of the basic side of Excel. Our students have to learn that anyway because it's a product and a tool they use in industry, and so We do
Mhm.
use some of the t-testing and things like that as well, but I haven't done the ANOVAs too much yet. So that's something I'll take a look at.
Essentially, we're building a table. So the ANOVA table that you see in States, where it's sum of squares and degrees of freedom and mean square, we build that in Excel, and then there's a single column that they have to put the letter N in for no. Does this term look significant? And as soon as they put no in, then it starts summing the degrees of freedom in the degrees of freedom in sums of squares. And then we can calculate F, and then from that we calculate the probability of the p-value. So, but that's all built manually into Excel, and then every time they put an experiment, they have to decide themselves using the half normal plot. Does this look significant? Does this look significant? Essentially, the poor man's version of States. Just click on these buttons and you'll get it.
Yeah. So Rachel, you'd ask about the software we use. We do use States Design Experts, and that for us, I guess what I really like about that, and I've seen some other folks that do teach design of experiments closer here around Rapid City, and what I like about States and the Design Expert is it really leads you through that, and so it's made it easier for the students and also safer, so they don't get into places where they get things that are results that are confounded and so on. So for us, that's been really good. We just didn't have the time to spend a lot on the coursework, but it's been it gives the students a safe result, I guess.
I can absolutely echo what David just said. It's very intuitive way of analyzing the data, building the design, analyzing the data, and especially the diagnostics are very useful to identify also individual runs for which you may want to have a closer look on the primary data, like if there was any issue when you were transferring the data from your data acquisitions sheet into the software, or any problems with the measurements. I think that also really helps, and helps teaching the students understand the importance of looking at the primary data and any data manipulation that comes in between the data acquisition and when you toss the data into Design Expert. I mean, the Catapult data is quite intuitive. There's not much to be manipulated, but some of our data are based on image analysis. And so depending on how you analyze the image, the result can be very different. And that is an important thing to teach. Then coming to the other softwares that we use, it could be R, but mostly it's Python. So we export data from Design Expert and then manipulate it to be actually usable in our experiments. So some of the factors that we have in Design Expert may not be one-to-one translatable into the experiment. So we need to do some adjustments first. Giving an example could be chemicals. So sometimes we want to look at the individual components of a chemical, which are the parameters in Design Expert, but then when we use it in the laboratory, we need to make some compromises because some salts exist only in specific ion combinations, and that needs to be translated back into what we actually use in the experiment. So that's done using Python code, for example.
And at St. Thomas, we use Montgomery's DOE textbook. We lecture out of the textbook, but it's very practical and focused on case studies, as I mentioned. And then St. Thomas purchases a hosted license from States. That works fantastic. And so students have access to Design Expert. And we use Design Expert because it's very comprehensive. And you just cannot beat it for ease of use. And our students see that directly, especially the ones that come in from industry with some DOE experience with other software, and they highly appreciate the ease of use of States Design Expert. And then in addition, I promote the Studies website, because that houses really excellent recorded webinars on a whole host of topics. There's probably dozens of recorded webinars on every chapter that we discuss. And then also I promote the tutorials, and there's PDFs, but we don't spend any time in class on that. Those are just pointed out for extra references for students.
Thomas,
You
what
get
was the
to
name
join
of
that.
Montgomery?
Oh, sorry, Mark, go ahead.
I just was asking Thomas to remind me again the title of Montgomery's book.
I think it's Design and Analysis of Experiments, and it's published by Wiley, and it's in the 10th edition. The 10th edition was published in 2020, so it's very up to date. And now we're in 2025, and I'm wondering if there's going to ever be an 11th edition, or who's going to publish the next comprehensive textbook on DOE. I don't know. And by the way, Mark, Yates' algorithm is in Box Hunter and Hunter for another reference to Yates' algorithm.
I have that one on my shelf. If you go to, well, several times I've gone to Studies and sat through some of their training. I did mixture designs. I did the basic one. I did something else. But Mark and Pat were just always handing out books. So that's where I got Box Hunter and Hunter. And then I also have, I think it's Cornell did mixture designs.
Yes.
If I remember right. That one sits on the shelf a little bit, but Johannes, I would think with what you're doing in the food industry, that mixture designs could be big for you. Are you doing anything with mixtures?
Yeah, a bit, because most of the time we're working with buffer compositions, and even though it is like in the lab you're preparing a mixture, but from an experimental or from a DOE perspective, most often we can treat that as regular numeric parameters, because they don't really affect each other. There's some classes of experiments like when we really have some liquids that we mix with one another. In that case, we do use mixture designs. Yeah.
So I do want to ask, since folks have mentioned both computer experiments and Python coding, are any of you using Studies 360 in class or just Design Expert?
Oh, I think we're using 360.
We're using Design Expert, and we'd rather use Stat 360 because that has computer experiments. That's what we're lacking in Design Expert. We don't need Python scripting. That's the last thing I'd like to do.
I think we use Design Expert, Rachel. Whatever you provided for us, so what we got.
Well,
So,
we do.
I had to go open mine, and the splash screen says 360. So I think sort of it's, Rachel, what you've provided is sort of what we do.
Yeah, no, for student licenses, we started only providing Studies 360 a couple years ago. So any student who is purchasing out of pocket will get all of those extra features to play with.
Nice.
So before we move into questions from the chat, is there anything else any of you want to add about the importance of teaching DOE at the university level?
Well, I'll just say from my experience in industry, I worked with thousands of scientists and engineers, and for me, the number one skill for them to become better scientists and engineers is design of experiments. And I saw that all throughout my career. Those were the most valuable scientists and engineers for our company.
Well, I would like to state it's highly underrated in our courses of study, in our curricula. So when I was studying, which is already a while back, but we didn't ever touch the topic at all. So when I started my PhD in 2009, that was the first time I was exposed to design of experiments. And I've been using Design Expert ever since. And when I had the first opportunity to give my own classes, it was the first course I designed, because I thought this is a topic we need to have in the curriculum. So now from being completely elective, it's now like mandatory elective in the current curriculum. And I would expect that more than half of the students will have one or the other DOE class now. So from 0 to 50%, I think is a good start.
I remember the first time I came to Studies for training, which was the basic, the entry level, and so we're all in the conference room and we go around and we introduced ourselves. And I said that I was at Fair State and I'm learning to teach this class. It was really greeted with a lot of surprise. Sort of everyone else in the room said, we've looked to find universities that will teach this and we're just not finding them. And so that sort of heartened me to know that, well, at least we are in our little corner of Michigan, and all the type of manufacturing that goes on in Michigan, of course, automotive, furniture industry is huge here. That those people in particular are interested in hiring people with these skills. And I tell my students, you've taken one class. Wherever you go to work, you're now going to be the guru. And I've had students who've gone on to jobs, and once they find out they can do design experiments, that sort of becomes their exclusive job, is going around and helping different groups set up and run design experiments. So it has proven to be a real separator for our graduates in terms of getting a job and being able to contribute when they get there.
Yeah, I agree. I tell our students that they're very rare, in the sense that there are very few engineers in industry that have ever taken a semester-long course in design of experiments. Most engineers in industry get trained after they arrive in the company through internal trainings. I delivered the internal trainings for decades, and that was an introduction, really. It was getting people exposed to the strength of experimental design.
Yeah, and I'll echo that, what you just said, Tom and Mark. In the chemical engineering departments, I think there's 170 in the US or something like that. There's not a lot that introduce their students to design of experiments unless the students have that desire. But I also hear back from industry the same sort of thing you were saying, Tom and Mark, that they really appreciate the engineers that have that experience, or at least have been exposed to it. And we have a local chemie that has his own company here in town, and he's always saying, you're still teaching that class. So we're to that point now where we're having discussions, how can we carve out some of our curriculum to make this a mandatory core, like you're having, Johannes. That's our goal, I think, is to do that.
Thank you very much. Okay, so I see one hand. If you can go ahead, and anyone who has questions, there is both a chat and a question bar on the top right of your GoToWebinar screen. Please put your questions there and our experts will answer them. In the meantime, I can go over the questions that came in during the presentation. There was one person who asked about a certificate of attendance. You should email Studies about that, and we can take care of that over email. Mark Anderson is on the line today and has enjoyed the conversation very much. He said, for Mark Rusko, a great blast from the past with mentioning the Yates algorithm. When he started doing DOE in 1974, they used this for effect calculations. No PCs then, just slide rules and pencil and paper. It's got to be even more difficult than Excel.
Yeah, because it does. It gets you directly to the half effect, the slope, and then the second column, it gives you the sum of squares, which is really the beauty of doing it. It's not really necessary anymore, but with the advent of Studies and of course Excel, but it sure is an interesting thing to think about, that Yates was developing this probably as Fisher is developing all his tools and techniques, and inventing ANOVA, that Yates is just in there shaking his head, goes, I know who's going to have to do all this work, and it ain't going to be me. And so it's one thing to sit and see what he did in reverse engineering, to see, okay, I see how he did that. But to come up with it is just remarkable. in a day, of course, in that decade, there was nothing but slide rules and math tables to look things up in.
While we're waiting for questions from the audience, do any of you have questions for each other?
I'm interested to hear from Johannes more about how you're applying all this in the food industry, because we don't have much. Well, there is some food industry here in Michigan, of course. In fact, a couple weeks ago, I visited one of my students at a place that made frozen waffles. I don't know if you've ever seen frozen waffles made, but they make 517 waffles a minute at this company. So I don't have much experience with food.
So personally, I work mostly with biotech, so we are developing pharmaceutical products. But just because I attended one DOE conference organized from studies / the cooperation partner in Europe, and there was one person from the food industry, and they really did DOE when testing like convenience foods, like microwave, heatable, ready to use food preparations, and that worked out for them. So they optimized like the chunkiness of the sauces, etc., based on the feedback of a test panel of, I think, 250 persons. What we do is we optimize different process parameters. So for example, we process plant material and we want to identify how can we get most of the protein out of the plant material for our further processing. So that would be extraction conditions, and then we optimize freezing procedures. How can you preserve living cells when you expose them to extreme low temperatures? So essentially all sorts of things, because most of our processes are dependent on many different parameters. In many cases, we know already which are the relevant ones. So what you said earlier, Mark, that you would focus mostly on the two-level factorial designs. For us, it's more the response surface methodologies that we're interested in, because many of the parameters that have an impact are already quite established, and we need to optimize for the different conditions. Yeah.
My apologies. I thought I'd remembered in your
No worries. All good. No offense taken here.
Okay, thank you. I'm interested in how are you guys addressing though the word just slipped out of my mind, when you convert your data. Rachel, what is that called in studies, where right at the beginning you said you want to transformations? Yes. How are you addressing that with students? Because my students never quite understand what's going on with those.
Well, we just look in the lower left corner of the diagnostics and see.
Just don't do that, because that's what we want to do.
Whatever it recommends, we go try it.
Mm-hmm.
It's usually better.
Okay.
What I tell them is like because they have heard statistic courses, and so I mean the base things that they can remember is that for most of the statistical tests that you do, you need equal variances, or at least variances that are about similar. And so if you can tell them if the error is not like a fixed offset like plus minus XYZ, but a percentage, then you don't have equal variances inherently, because as the value that you measure gets larger, the error is getting larger. And then to make sure that you have a similar error in all the regions of your design, if you do the transformation, they're not becoming perfectly equal, but better. And so the reliability of the tests that you do increases. This is how we try to convey the message.
Right. And then are you going off and looking at the diagnostic plots to look for improvement? Because that's sort of where we go. Yeah.
Exactly. Yep.
So we do have a question from Dr. Wolfgang Becker, that he works at a German research institute and has been promoting DOE for years. However, the problem always arises that many people think it's unnecessary because it's an exotic topic. How should we deal with this problem?
My response would be challenge. To say, okay, you here's the problem. You follow your path to solve it, and I'm going to do a DOE, and let's see who gets to the answer more quickly and more reliably. And the problem is, if you do that a few times, people can luck onto the answer pretty quickly and go, see, my method of guessing is better. So you're going to have to do it several times. But what I have found over and over is that DOE leads me more quickly to a solution that I can use every single time, as opposed to, well, you guessed that time, so next time you're just going to guess again. And I remember I did that in particular. We were having a problem with an assembled part when I was still in industry, and literally the one group went off and to do theirs, and we were working through it very methodically with some experimentation. And we both eventually arrived at the same point, which was, oh, this is actually a part that we were purchasing. It was a plastic injection molded part. So my group got in our cars and we drove to that injection molder, and we were there measuring parts when the other group arrived to investigate that part. So it was very clear that it was leading us more quickly to the solution. So I don't know if you can pull that off in your situation, but that would be one suggestion.
And I actually recently read a book on the topic, and the title of the book, are you ready? Apes in Lab Coats. I highly recommend that book.
He's got a LinkedIn blog that he does too.
But that book is on the topic of the question. That book answers the question.
From my experience in industry, we had a limited time for the number of experiments we could do. We were on a time crunch, and DOE would organize for us what we were trying to do and minimize the number of experiments that we could do, but also in an organized fashion. And then also getting the confidence that what we are seeing as results make sense, and that there is a real, if we change a factor, for instance, there's a realness to the fact that it's influencing the result. So having some basis to say that our results make sense, and that these factors matter, these don't. And so for us, that was very helpful and encouraging to know. Right.
I would also like to second what Mark said. So I think it can be fairly easy to show that, and also what Dave said, that you can save a lot of efforts and that you can get reliably to where the optimum of a process is with fewer experiments. So for example, if you think of just a 2-parameter setting where the parameters interact with each other, and you would do the one factor at a time approach, the impact of the more or less random starting point can be quite severe and will lead you maybe to a very suboptimal setting. Whereas it's very easy to show that with the DOE, you can, with fewer samples, you can actually get a better idea of your design space or of your parameter space and identify the optimum more reliably and with less effort. I think that's a very easy graphic to show and say, okay, how do you beat this? You don't.
So Leonard Lai is on the call today as well and wants to give his thanks to Tom for buying the DOE Golfer and finding it useful.
Yeah, thank you, Leonard.
All right, we are past the hour, so I'm going to go ahead and wrap this up. Thank you very much to all of you. Thank you very much to the folks who chimed in the chat. This has been a really enlightening discussion. I will go ahead and post the recording to our YouTube channel with a collection of the recommendations you all made with regards to books and experiments. And that'll be in the description of the video. So that'll be up as soon as GoTo processes this recording for us. Any final thoughts you guys want to leave for food for thought for everyone?
I would say that the answer is almost the answer for everything. Don't wonder about it. Just go and try it. If you're trying to get into DOE, just set one up and go see what happens. Almost every time you do an experiment, you'll get to the end and go, man, I wish I would have known that when I started. So don't put all your resources into the first one, but just try it and just see how it's going to turn out.
Do is in DOE, right? It's part of the word. So I agree to it.
Okay. Thank
All
you,
right,
everybody.
Rachel, thanks for setting us up.
Yeah, of course. This has been really
Thanks a lot.
wonderful. Yeah. So have a great rest of your Wednesday, everyone.